Hi, this is Module 15 of Applications in Engineering Mechanics. Today we're going to continue with what we started last time and actually sketch a shear force diagram for a multi-force member. So here's the generic beam situation that I laid out last time. We looked at the free body diagram of a differential element, and we came up with the following relationships. We found that the negative value of the load at any point equals the slope or the rate of change of the shear diagram. And we found that the change in shear between 2 points equals the negative of the area under the load curve. And so what I'd like to do now is to apply that theory, if you will, to this beam as loaded as shown and come up with the shear force diagram. So we know on this beam all of these applied external forces and moments. The only thing we don't know at this point is the reactions at the roller constraint and the pin constraint. So I'd like you to start off by determining the external reactions at point C here at the roller and point F at the pin on your own. And by now you ought to be real experts at this, given your background from the first course, Introduction to Engineering Mechanics, and what we've done so far in this course. So you should be able to knock this out quite handily. When you have that done, come on back. Okay, here's the results you should have come up with and the equations of equilibrium I used to get them. I found F sub y is 11,000 pounds out here on the right, and C sub y is equal to 21,000. And since there's no forces in the x direction, there was no x reaction force at point F. Okay, now knowing those, there's my beam with all the loads and this moment being applied. We're going to work on the bending moment diagram in the next modules. But for this case now, we'll use these relationships for the shear diagram. And so for the shear diagram, as we come along and we're looking at the material to the right, we have 0 up until we get to the end of the beam. So we start off at 0. And at the end of the beam, we see that we have this 10,000 pound shear force. And it's acting counterclockwise on the right side of my material, just like this situation over here. So that's going to be negative. And so the shear force immediately drops down to minus 10,000. And now we don't have any change in the shear between points A and C. There's no other shear forces being applied. There is a moment, but that's not going to affect the shear force. And so we go out to point C here, and the shear force diagram stays at minus 10,000 pounds. At that point, we have our external reaction from the roller that's up 21,000 pounds. And again, we keep looking to the right on the material, so that's up. It's going to be a positive shear force. And so we're going to change from minus 10,000 up to a positive 11,000. And then we're going to go from point C now to point D. During that interval, we know that the change in shear is going to be equal to the area under the load curve. And I found the area under the load curve. It's just a triangular area. And the total load under the area under the load curve is going to be 6,000 pounds. So we know that at point D, the shear force is going to be 6,000 pounds less than 11,000, or that'll be 5,000 pounds. Now, the shape of that curve in between those 2 points, we know at any point along that distance, minus the value of the load is equal to the change or the slope of the shear diagram. And so the slope of the shear diagram, the load here is 0, and it goes up to minus 6,000. So it gets greater and greater and greater in a negative sense. And so here we start off with a slope of 0, and it becomes more and more negative until we get down to 4,000. And so we've integrated a ramp function here, so this becomes a parabola function. I'm going to label that as P for parabola. By the way, down here in going from point A to point C, that was a straight line, so I'm just going to label that with S. Now again, between D and E we have no shear forces, and so no shear force changes, and so we're going to go from D to E as a straight line. And then going from E to F, the area under the load curve is 16,000, so that means the change in shear will be from 5,000 down to minus 11,000. We're going to be down here at minus 11,000. And between those 2 points, the negative of the value of load stays constant at 4,000, so the slope of the shear diagram is going to stay constant, and it's going to go down with a straight line here. And so that's a straight curve. And then finally, we're going to go up at the end, 11,000. That's positive, and it closes off at 0. And you should close off at 0 on both ends of your shear diagram. The only other thing you might want to do is you might want to find this distance where the shear force ended up switching through and was 0. And so let's use these two similar triangles to find that distance. We'll use this triangle and this triangle. And so we've got this side, this length is 4. And we're going to compare it to this length here, which we'll call x. So x is to 4, as this drop was 16,000. Actually, we'll just call it 16. We'll keep the thousands off. That'll be easy. And just to 5,000. I mean, you could do 16,000 to 5,000 or 5 to 16. Either way is fine. If you solve for x, then you find this distance x is 1.25 feet. The total distance is 4, so that means this distance is 2.75 feet. So now we know the value of the shear, the internal value of the shear force anywhere along the beam, and we would use that in designing the beam. You can see on your own where would be the cases where you'd have the maximum shear that you'd have to design for. Take a minute and think about that. Come on back. Okay, those locations, the worst case is here at point C, where I have a shear force of 11,000, or here at point F, where I have a shear force of minus 11,000. Here's another large shear force. You can see we actually have no shear, as I said, at this point right here, but we've got a very good sense of how the shear varies over the entire length of the beam. And so this is just a clean copy of what I just did so that you can see it. And that's it for shear force diagrams.